is a very important topic as it's applied in digital circuits designing and logic derivation. So in this series of tutorials, we'll be looking into the concept of Boolean algebra and understand its rules and laws. We'll understand the working of digital systems and understand how Boolean algebra is applied in these digital systems. We'll also see in the working of logic gates and how they operate in digital circuits. So with that being said, let's get started with this tutorial. In this tutorial, we'll be understanding digital systems and circuits. We'll see the concept of Boolean algebra and learn some of its rules. So let's understand what a digital system or a circuit means. Digital systems or circuits are systems that function with digital signals. Now digital signals are discrete signals typically having only two states, that is high state and low state, usually denoted by the binary number 1 and 0 respectively. So let me quickly show you an example of digital circuit. Okay, so as you can see, the first diagram is an analog signal, which means that this curve that I've just drawn is an alternating current which varies from -5 to +5 volts. Now this is termed as an analog signal. Now the devices that operate on digital signals such as your smartphones, laptops have this waveform. This is called a digital signal. Now a digital signal has only two values, that is 0 and 1, which usually corresponds to the 0 volts and 1 corresponds to the higher volts, say for example in this case 5 volts. So all the digital devices such as your smartphones, laptops and other devices usually operate on these digital signals. Now I have drawn a basic example of a digital circuit. We have a battery, we have a switch, we have a bulb over here, and there is some resistance to that circuit. Now when this switch is closed, electricity flows from positive to negative and this bulb starts glowing. As soon as I off the switch again or break the connection, electricity stops flowing and the bulb stops glowing. So in this case we are applying a digital signal which is +5 volts in this case for example, and we are switching it on and off. So we are switching from +5 volts to 0 volts, again back to +5 volts to 0 volts. So this is the reason why I drew this waveform. So now that you understand what a digital circuit is and what are digital signals, let's move on to understanding the concept of Boolean algebra. Boolean algebra is a branch of algebra in which the values of the variables are truth values, true and false, usually denoted by 1 and 0. It was first introduced by George Boole in 1847. Boolean algebra is widely used in development of digital electronics and systems, and it's not just applied to digital systems but also used in sets and stats. In fact, it can be applied to any systems which operate on two states which are opposite to each other, for example on and off, open close, true and false, etc. Now since digital circuits usually operate only on two signals or two states, we can apply Boolean algebra concepts and rules and laws to derive equations. We'll look into the equations in further tutorials. So now that you have a good idea about Boolean algebra and its concept, let's take a look at some of the rules of Boolean algebra. Variables in Boolean algebra can only have two values, binary 1 for high value and binary 0 for low. Complement of a variable is represented by an over bar. Now complement is opposite, so complement of 1 would be 0 and complement of 0 would be 1. Logical OR operation is represented by a plus between variables, example a plus b. So we read it as a or b and not a plus b. It is similar to addition but has slight variation. A logical AND operation is represented by dot between the variables, as you can see on the screen, a dot b, but we pronounce or spell it as a and b. It is similar to multiplication. Now we'll see these operations in further tutorials, so don't worry, these ideas will be very clear to you. Okay, so what we learned in this video, we understood what digital systems and circuits are. We saw the concept of Boolean algebra and how it is applied in digital circuits. We also saw some rules of Boolean algebra which we will be using in further tutorials while solving numericals. So that's it for this video guys. If you like this video, give it a thumbs up and share it with your friends. Also make sure you subscribe to our channel so that you get notified when we upload the next video. If you have any doubts or comments, do post them in the comment section below. Peace. Hey, what's up guys, Tanmay here for Simple Snippets. So this is the second tutorial for our video playlist Boolean Algebra and Logic Gates. In the previous video, we saw the concept of Boolean Algebra and also understood what a digital circuit and system means. So if you have missed that, you can check it out. In this video tutorial, we'll learn some basic operations of Boolean algebra. So let's get started. Today we are going to be looking into three different Boolean algebraic operations. The first one is a logical OR operation, the second is logical AND, and the third one is a logical NOT operation. So let's start with logical OR operation. Consider two variables. Now we know since it is Boolean algebra, these variables can only take up two values, that is 0 and 1. Now the logical OR operation is given as follows: A or B. Now the plus sign here is pronounced as OR because it is a logical OR operation and not a typical addition. So consider case 1. We take the values of A and B as 0 and 0. Now the OR operation between 0 or 0 is equal to 0. Consider case 2. Here we consider B's value as 1. Now the logical OR operation works similar to the addition operation. So 0 or 1 is equal to 1. Now let's see case 3, where we consider A's value to be 1 and B's value to be 0. Again 1 or 0 is equal to 1. Let's see case 4, where we consider A and B both to be 1. Now here 1 or 1 is equal to 1. So this is different from the typical algebraic addition operation, wherein we have 1 plus 1 which equals to 2. But a logical OR operation between 1 or 1 will always give again 1. Now to summarize all these cases, we have a truth table. A truth table is a table which has all the possible inputs of the variables and its corresponding outputs. So as you can see, the first two columns are the variables A and B with the different values, and the third column Y, which is the output, or the right hand side, which is the operation A or B. So we'll be using these truth table values and we'll be drawing these truth tables in our further tutorials as well when we solve some numericals. Okay, so now let's have a look at logical AND operation. We again consider two variables A and B. Now the logical AND operation is denoted by the symbol dot between the two variables, and it is pronounced as A and B. So again we'll have these four cases. For the case 1, we have A and B value to be 0. Now this logical AND operation works like a algebraic multiplication. So 0 and 0 will give us 0. Consider case 2, where we consider B's value to be 1. So 0 and 1 is again equal to 0, because if we consider it to be a similar as multiplication value, 1 into 0 will always give us 0. Let's see case 3. We consider A's value to be 1 and B's value to be 0. So 1 and 0 will give us 0 again. In the last case, where we consider both A and B to be 1, the value or the answer 1, since 1 and 1 is equal to 1. Now summarizing all these cases in the form of truth table, so we have the first and second column to be the input values A and B, and the third one to be the RHS or the output as shown. Now let's have a look at the logical NOT operation. Now the logical NOT operation works only on a single variable. So we consider the variable A. The logical NOT operation is denoted by the symbol A is equal to A with an apostrophe or an overhead bar. In this case I have used apostrophe, but we will be using overhead bar usually to denoting the complement. So whenever we apply a NOT operation to any variable, we get its corresponding opposite value. So for example, if A is 0, A complement will be 1. So let's see case 1. When A is equal to 0, the complement or logical NOT operation performed on that variable will give us value 1. And if A is equal to 1, A complement will be 0. Summarizing this into the truth table, we have the first column to be the A values and the second to be the RHS, that is the complement of A values, which is exactly opposite. So that's it for this video. So in this video, we learned the basic operations of Boolean algebra which we will be using throughout our tutorials, and these operations are very important because they are used in almost all these numericals. So that's it for this video, guys. If you like this video, give it a thumbs up and share it with your friends. Also make sure you subscribe to our channel so that you get notified when we upload new videos. Peace. Hey, what's up guys, Tanmay here for our channel Simple Snippets. So in this video tutorial, we'll be talking about the laws of Boolean algebra. Now I've divided this in two parts since we are going to be discussing about 10 different Boolean algebraic laws. So I've made two parts. In the first part, we'll be discussing the first 5 and the next we'll discuss the other 5. In the previous video, we discussed about the Boolean algebraic operations such as OR operation and NOT operation. So if you have missed that, you can check it out as we'll be needing them in this as well as in the upcoming videos. So let's get started with today's tutorial. Now as I mentioned, we'll be looking into 5 different laws of Boolean algebra. Now these laws are very important and they are the fundamental building blocks of Boolean algebra, and we'll be requiring them throughout this tutorial series. So make sure you have a good idea about these laws. So let's start with identity law. Now this is the table wherein we'll be discussing the 10 different laws. So we'll be discussing the first column of laws in this video. So let's start with identity law. Consider a variable a. Since it's a Boolean variable, it will have only two values, 0 or 1. Now here's the expression, a or 0 is equal to a. So let's see the LHS and RHS. Now the LHS is a or 0. So if a's value is 0, we get 0 or 0, which is again equal to 0. So case 1 is proved. Now consider a's value to be 1. In this case, 1 or 0 will give us the answer 1. So as you can see, the LHS is equal to RHS. So as the value of a changes, the value of LHS and RHS both changes and it is equal to the value of a. Now here's the expression 2. A and 1 is equal to a. So let's see the two cases. Consider a's value to be 0. Now 0 and 1 will give us value 0. So the first case is proved. When a is equal to 1, we know 1 and 1 will give us 1. So the second case is also proved. Now if you don't know these operations, we've discussed them in the previous video. That is the reason why I told you to check them out. Summarizing them in the truth table values, we have the two expressions. Now we've written the LHS in the right side column and the RHS in the left side column. As you can see, those values are equal. So this expression is proved. Now let's see the idempotent law. Again consider a variable a. Now the expression 1 is a or a is equal to a. Well, the expression itself is pretty self-explanatory, and you can see when we substitute a equal to 0, we get 0 or 0 and the LHS is equal to RHS. When a equals to 1, we have 1 or 1, which is again equal to 1. So these two cases are proved. Here's the expression 2. We have a and a equal to a. So when we have a equal to 0, we get the RHS as 0. And when we have a equal to 1, we again get the RHS as 1. So here are the truth tables for these two expressions. As you can see, the values of LHS and RHS are equal. So these expressions are justified. Now moving ahead to dominance law. Here's the expression 1. We have a or 1 equals to 1. So you can observe no matter what the value of a, we always get the answer as 1. That is, 1 is dominating the variable's value a. So in the first case, when we have a equal to 0, we get 0 or 1, which is again 1. And when we substitute a equals to 1, we have 1 or 1, which is again equal to 1. So here 1 dominates the value of a. Let's say expression 2. We have a and 0 equals to 0. Again 0 dominates the value of a. That is, no matter what we substitute as a, we always get the answer 0. So in case 1, we substitute a equals to 0 and we end up with the value 0. In case 2, we substitute a equals to 1 but we still end up with value 0. That is the reason why this law is named as dominance law. Here's the truth tables of these two expressions. As you can see, in this case, the LHS is not equal to RHS, but it is dependent on the dominant value. So in the first case, 1 is the dominant value, so we always get the answer as 1. In the second case, 0 is the dominant value, so we always get 0 as the answer in the RHS. So let's move on to involution or double negation law. Double negation means taking 2 times complement of the same variable. We know complement of variable inverts the value. So if a is equal to 1, its complement is equal to 0. Now double complement means that we take the complement 2 times. So in the case 1, you can see expression 1, a double complement is equal to a. Let's prove this. For case 1, consider a equal to 0. Now taking 1 time complement, we get answer 1. And again taking its complement, we get again answer 0. That was the value of a in the first case. For the case second, we consider value of a is equal to 1. When we take one time complement, we get answer as 0. And when we take the second time complement, we again get back the answer 1, which is what we substituted a with. So expression 1 is justified. Here's the truth table for that expression. As you can see, the LHS is equal to RHS. Now let's have a look at the fifth law, that is negation or complement law. Here's the expression to that law. It says a or a complement is equal to 1. So when we substitute value of a as 0, we know a complement will be 1. And when we perform a logical OR between 0 and 1, we always get an answer as 1. So the first case is justified. When we substitute value of a as 1, we know a complement will be 0. So we have 1 or 0, which again gives us value 1. So the second case is also justified. For the expression 2, we have a and a complement, which is equal to 0. In case 1, we substitute a's value to be 0, so the complement will be 1. Now we know 0 and 1 will always give us 0. So the first case is justified. In the second case, we consider a's value to be 1, so the a complement would be 0. And the entire expression would be 1 and 0, which will again give us the value 0. So the case 2 is also justified. So here are the truth tables. As you can see in the truth table 1, no matter what the value of a, we always end up with RHS as 1. And in the truth table 2, no matter what the value of a, we end up with value of RHS as 0. So that's it for this video, guys. We still have to cover 5 more laws, but I thought of making a separate part of it because this video was getting too lengthy. So we'll cover those 5 laws in the next video. If you like this video, give it a thumbs up, and if you have any queries, you can put them in the comment section below. Also share it with your friends and subscribe to our channel so that you get notified when we upload the part 2. Peace. Hey, what's up guys, Tanmay here for our channel Simple Snippets. So this is the 4th video tutorial for a playlist Boolean Algebra and Logic Gates. Now this is the part 2, and in part 1 we discussed 5 different Boolean algebraic laws. So if you have missed them, you can check it out. In this video tutorial, we'll be discussing 4 different laws: the commutative law, associative law, distributive law and absorption law. So as you can see in the table in the previous video, we learned the first 5 different laws, that is identity law, idempotent law, dominance law, involution or double negation law and negation law. And in this video, we'll be discussing the laws from 6th to 9th. The 10th law, that is the De Morgan's theorem or De Morgan's law, we'll be discussing in a separate video, starting from commutative law. Consider 2 variables a and b, and since these variables are Boolean algebraic variables, they'll be taking only 2 values, that is 0 and 1. So here's the expression 1, a or b is equal to b or a. And the expression 2 is a and b is equal to b and a. Well, the expression itself are self-explanatory, but let's see the truth table values. For the first expression, we have the 4 cases, wherein in the first 2 columns we have the a and b values, and the next 2 columns are the LHS and RHS respectively. As you can see, the values match, that is, the expression 1 is proved. Let's see the second truth table for the expression 2. Again here we have the first 2 columns as the input values a and b, and the next 2 columns as the LHS and RHS respectively. Also, as the LHS is equal to RHS in all 4 cases, we have proved the expression 2. So now let's move on to the next law. So the next law is associative law. As you can see, there are 3 variables in this law, a, b and c. So here the number of variables or the number of variations of input is equal to 2 raised to n, where n corresponds to the number of variables. By this I mean the number of possible input variations are to the power of 2 raised to n, where n is the number of variables. So in this case, n is 3, as we have 3 different variables. So the possible variations would be 2 raised to n, which is 2 raised to 3, which gives us the value 8. So as you can see in the table, we have 8 different rows created for these truth tables. Now let's start proving the first expression. This is our first expression. A or b or c is equal to a or b or c. So let's first start the input variable values. For the first variable a, I write 4 times 0, then 4 times 1. For the next variable b, I write 2 times 0, 2 times 1, again 2 times 0 and 2 times 1. For the last variable c, I write 0, 1, 0, 1 alternatively. And this covers all the possible variations of input values. Now let's calculate b or c. For the first case, we have b or c as 0 because b and c both are 0. Let's calculate a or b. Again a or b is 0 as we have both the values of a or b 0. Now the LHS is this entire part. So it is made up of a and B or C together, that is this part and this part. We just need to take an OR of these two parts. So we need to take 0 or 0, which will again give us 0. For RHS, we have this part and this part, as you can see in the expression. So we need to take an OR between these two. So this 0 or C, which is again 0. So again we have 0. So here we have LHS equals to RHS. Similarly, we have to calculate for all these other 7 cases. So I'll just quickly calculate by applying the basic Boolean algebraic operations, that is OR and AND operations. In this case, we'll be using only OR operations. B or C for case 2 is 1, A or B is 0. So LHS would be 1 and RHS would also be 1. So I'll just fill out these values, and in the end we'll cross check whether LHS is equal to RHS. Okay, so I'm done completing this table. So as you can see, if you compare the LHS and RHS columns, all the values are equal to each other. That is, in all cases they are equal to one another, so proving that this expression is correct. So we just proved one expression. Let's go ahead and prove with other expression. Now again, first I'll fill up the variable values. So I'll just repeat again. For the value A, I write 4 times 0, then 4 times 1. For variable value B, I write 2 times 0, 2 times 1, and repeat that. And for variable C, I write 0, 1 alternatively. Now in the LHS, we have a part B dot C or B and C. So I separately calculate that in this column. For the RHS, we have a component A and B separately. So I calculate that again in this column. And then in the end, we again calculate LHS and RHS. So let me just quickly calculate these values. Okay, so I have calculated the values, and as you can see, the LHS is always equal to RHS in all cases, hence proving this expression. Now if you don't know the logical AND operation or logical OR operation, you can check out the previous videos where we have discussed these basic operations. So let's move on to the next law. Okay, so the next law is distributive law. As you can see, we have 3 different variables A, B and C. So the number of input values will be 2 raised to 3, which equals to 8. So as you can see in the truth tables, I have written the values of A, B and C as follows. So let's have a look at the equation 1. So we have this as LHS and this as the RHS, and we need to prove that these two are equal. So in the LHS part, we have an individual value A and we have a combination of B and C. So I calculate B and C first, and to calculate B and C, we need to take a logical AND operation between variable B and C. So let's take a logical AND operation between them. Okay, so now we have calculated B and C. So to calculate the LHS completely, we need to take an OR operation between this entire component and this A. So we need to take a logical OR operation between this column and this column. So the result will be as LHS over here. So let me just calculate the LHS. Now if you don't know how to calculate logical AND or logical OR operations, just take a look at the previous videos in this playlist, because we'll be needing them throughout these lectures. Okay, so now we have got the LHS. Now let's take a look at the RHS. We have the component A or B, and we have one more component A or C. So I have calculated them separately. So let me just calculate its values. Okay, so I have calculated the individual components of the RHS, that is these two components. So now to calculate the entire RHS, we just need to take a logical AND operation between these two values. So let me just take the AND operation. Okay, so now that we have calculated both LHS and RHS, we just need to compare these two columns. Now as you can see, the values in LHS are equal to RHS. Hence we have proved that this equation is true. So now let's move on with the next equation. In the next equation, we have LHS as A and this entire component B or C. So I calculate B or C separately first. So let me just calculate the OR operation between B and C. Now to calculate the LHS, we just need to take a logical AND operation between operator A or variable A and this entire component. So calculating the AND operation to get the LHS in this column. Okay, so I have calculated the LHS now. Let's have a look at the RHS. In the RHS, we have two components, A and B and A and C. So I have written them separately in these two columns. So let me just calculate these separately. So as you can see, we have calculated the separate components A dot B and A dot C. So we just need to take a logical OR operation to get the entire LHS. So I'll just calculate the entire RHS. Okay, so here are the values of RHS. Now comparing LHS and RHS, we can see that for each case LHS is equal to RHS. Hence this equation is proved. So now let's move ahead to the next law. Okay, so the next law is known as the absorption law. Since there are only two variables involved in these laws, okay, cut that. Since there are only two variables involved in this law, the number of input variables or the number of input values would be 2 raised to 2, which is equal to 4. So let me just write down the input values. So I have now written down the input values of both the equations. So let's have a look at equation 1. In equation 1, we have two components. We have an individual variable A and we have a component A or B. So I calculate A or B separately first. So I'll just calculate the values. Now to get the LHS, we just have to take a logical AND operation between A and this component. So calculating the LHS. Okay, so now we have calculated the LHS. Now for the RHS, we just have the value of variable A. Now we have already written down the value of A, as you can see in this column. So I just need to repeat it again in RHS. I'll write it down as it is. Comparing LHS and RHS, you can see that for each value in LHS, we have an equivalent value in RHS. Hence this equation is proved. So let's move on to the next equation. In the next equation, we have a separate value A and a component A and B together. So let me just first calculate A and B in this column. Now for the LHS, we need to take a logical OR operation between the variable A and this entire component. That is, we need to take a logical OR operation between this column and this column. So calculating that, we get okay, so I have calculated the LHS. Now for the RHS, we simply have the value of variable A. So I'll just write down as it is. And comparing the LHS and RHS, we can see that LHS is equal to RHS. So this equation is also proved. So that's it for this video, guys. So in this video, we learned the 4 different Boolean algebraic laws. Now in the next video, we'll learn the De Morgan's law. If you like this video, give it a thumbs up and share it with your friends. Also make sure to subscribe to this channel so that you get notified when we upload the next videos. Peace. Hey, what's up guys, Tanmay here, back with another video for our channel Simple Snippets. So in this video, we're going to be learning the De Morgan's law. In the previous 2 video tutorials, we saw the Boolean algebraic laws, which are the fundamental laws. So I decided to create a separate video for the De Morgan's law as they don't fall under the same category. So let's have a look at the De Morgan's law. So here are the 2 expressions of the De Morgan's law. The first expression is as follows. A or B the whole complement is equal to A complement and B complement. The second expression or equation is A and B the whole complement is equal to A complement or B complement. So let's go ahead and prove these. Okay, so as you can see on the screen, I have the 2 different expressions written with their truth tables respectively. So since there are only 2 variables involved in these laws, the number of possible inputs or input variations is 2 raised to 2, which is equal to 4. So I have also written down the input values, that is A and B, in the truth tables below. So let's have a look at the first expression. Now in the first equation, we have an LHS part and we have an RHS part. So let's see the RHS part. For the RHS part, we need A complement, we need B complement, and we need an AND operation between these 2 values. So first let me calculate the complements of each of these variables individually. Now if you don't know how to calculate complement, or if you don't know the basic Boolean algebraic operations, that is OR operation and AND operation, you can check out the previous video tutorials wherein we have discussed all these operations. So since for the first case A is 0, its complement would be 1. Again it will be 1 in this case and 0 in the last two cases. Similarly for the B complement we have 1 0 1 0. So for the LHS part we have A or B the whole complement. So let's first calculate A or B. So we know the value of A or B will be 1 when any of the individual input variables is 1. So you are leaving the first case, all the three would be 1. But the LHS is complement of A or B. So we need to take complement of this to get the LHS over here. So it would be 1 and 3 times 0. Now for the RHS part, we need to take a logical AND operation between the two variables A complement and B complement. So we have calculated the individual variables A complement and B complement. We just need to take a logical AND operation between these two values. So the RHS would be, okay, so as you can see, the LHS and RHS is equal. Hence we have proved the first expression. Now let's move on to the next equation. In this equation we have A and B the whole complement. So we'll have to calculate A and B first. So you can see in this column I am doing that. And for the RHS part we have A complement or B complement. So we'll also need the values of A complement and B complement. So we are calculating them over here respectively. So let me just calculate all the complement values first. Now I'll calculate A and B. Remember that the value of A and B will be 1 when both the variables A and B will be 1. That is, if any of the value of the variable is 0, the resulting answer will also be 0. Okay, to calculate the LHS, we need to take the complement of this entire column. So let's calculate the LHS. We have 1, 1, 1 and 0. To calculate the RHS, we need to take an OR operation between A complement and B complement. We have calculated A complement and B complement individually. So we just need to take an OR operation between them. So I'll just calculate the RHS. Okay, so again, if you compare LHS and RHS, they both are equal. So again, we have proved this equation right. Thus we have proved both the De Morgan's laws. That's it for this video, guys. If you like this video, give it a thumbs up and share it with your friends. Also, if you have any queries or doubts, you can always post them in the comment section below. And make sure you subscribe to our channel so that you get notified when you upload the next video. And in the next video, we will be discussing about the logic gates and also see some basic logic gates. Peace. Hey, what's up guys, Tanmay here, back with another video for our channel Simple Snippets. So in this video, we'll be discussing about the concept of logic gates and see some basic gates. In the previous video, we discussed about the De Morgan's law, so if you have missed it, you can check it out. Okay, so let's get started with today's tutorial. In this video tutorial, we'll learn the concept of logic gates, we'll understand what exactly logic gates are, and we'll see the 4 different types of logic gates. That is the OR gate, AND gate, NOT gate and XOR gate or XOR gate. So let's start with understanding what exactly logic gates are. Logic gates are basic building blocks of any digital system or circuit. So they are basically digital circuits or electronic circuits which have one or more input but only one output. Now there is a certain relationship between the input and output, and depending on that we categorize them in types of logic gates which we just discussed before. Now there are 3 basic gates, that is AND, OR and NOT gate, and we'll also discuss the XOR gate, which does not fall under the basic category, but still it is a very important logic gate. So here's a pictorial description. As you can see, it's a transistor NOT gate. We have resistance as well as the transistor TR1 in the center. You can also see the LED glowing. So when the input is 0, the LED glows. Since this is a NOT gate, the LED glows only when the input value is low. So similarly, other logic gates have similar circuit designs. So let's see what exactly OR gate is. An OR gate performs a logical OR operation. We've seen the logical OR operation in our previous tutorials where we discussed the basic Boolean operations. So these operations are practically carried out by these logical circuits. The output is high, that is the output is 1 if any of the input is 1. The output is low if all the inputs are low. Now here's the expression. You must be familiar if you have checked out the previous videos. So the expression goes as follows. Output Y is equal to A or B. Now here's the symbol denotation of OR gate. A and B are the inputs. So this is an OR gate with two input values. It can also have more than two values, but for simplicity purpose I've just drawn two input values, and the output is as shown, y is equal to a or b. Also this is the truth table of an OR operation. So as you can see, only when the value of a and b is 0, the output is 0, and rest in all cases it is 1. So let's move on to the AND gate. So AND gate performs a logical AND operation. We also saw this operation in our previous tutorial, so if you have missed it, you can always check it out. In the AND gate operation, the output is high if all the inputs are high. That is, the output is always equal to 1 only when all the inputs are 1. And the output is 0 or low if any one input is 0 or low. So here's the expression. The output y is given by a and b. Now the logical circuit design denotation is shown on the screen. As you can see, it has two inputs a and b and one single output, which is given by y is equal to a and b. Here's the truth table for the AND gate or AND operation. The output y is high or is 1 only when a and b both are equal to 1. Rest in all cases the value is 0. Now let's have a look at the NOT gate. The NOT gate is a special gate, and by that I mean it has only single input and single output. It performs logical NOT operation. We've seen the NOT operation in the previous tutorials, and it performs similarly. That is, if you provide a 0 value, it inverts it to 1. If you provide 1, then it inverts it to 0. So the output y is high if input is low, and output is low if input is high. So it is also known as an inverter. Here's the expression. Y is equal to a complement. Here's the symbolic representation of the NOT gate. We have a single input a and single output y, which is equal to a complement. Here's the truth table for the NOT gate. As you can see, when a is 0, y is 1, and when a is 1, y is 0. That is, the values are inverted. Now let's have a look at the XOR gate. The XOR gate performs logical XOR operation. This is a special gate wherein the output y is high if odd number of inputs are high, and the output y is low if odd number of inputs are low. You'll understand this when we see the truth table. Now here's the output expression. Y is equal to a XOR b. It looks like an OR operation, but we have a circle around the OR symbol or the plus symbol. Here's the symbolic representation of the XOR gate. It is similar to the OR gate, but there is an extra curve where the inputs meet. As you can see, it is a two input XOR gate. That is, we have input values a and b and a single output y, which is equal to a XOR b. Now here's the truth table. So as I mentioned, the output is high when odd number of inputs are high. So in the case 2 and 3, we have only one input which is high. So that is the reason why the output is high. But in the case first and the last, odd number of inputs are not high. That is, in the first case, both the inputs are 0. So we end up with the output as 0. And in the last case, both the inputs are high. That is, even number of inputs are high. That is the reason why the output is 0. That's it for this video, guys. If you like this video, give it a thumbs up and share it with your friends. Also make sure you subscribe to our channel so that you get notified when you upload the next video. Also in the next video, we'll discuss about the universal gates. Now these gates are different from what we discussed in today's tutorial, and you'll understand them when you check out the video. Peace. Yo guys, Tanmay here for Simple Snippets, back with another video tutorial on Boolean algebra, logic gates, K-maps, and that tutorial series wherein we've covered all the concepts of Boolean algebra and all. So in this video tutorial, we'll be focusing on logic gate, especially one gate which I've missed out in this playlist, that is the XNOR gate. Now if you've been watching this video tutorial series, you must have seen we've covered almost all the gates and different Boolean algebra concepts as well, but then one of the users or subscribers of this channel recommended that I should cover the XNOR gate, and I pretty much forgot to cover that gate. So in this video tutorial, we'll be discussing through that particular topic. And if you are new on this channel, make sure you subscribe to this channel because there are a lot of information technology oriented video tutorials and more are coming soon, so you'll get notified whenever I upload a new video tutorial. So make sure you subscribe and turn on the notifications as well. So with that being said, let's get started with today's topic. So XNOR gate is not a basic gate. It is basically a combination of two gates, that is the XOR gate and the NOT gate. Now we've extensively covered both these gates in this video tutorial, which you can see on the top right corner. So if you don't know about these two gates, you can check it out. And we've also talked a bit theory about what logic gates are. So coming back to this topic, XNOR gate, you can see XNOR gate is a combination of XOR and NOT gate. So here you can see we have A and B as two inputs to XOR gate. Then the output Y is equal to A XOR B. So this is a
symbol of XOR. Now this output is now fed to a NOT gate as input. So you can see A and B, or A XOR B, is passed as an input to a NOT gate, which takes only one input and it complements that input and it gives an output. So you can see the output is going to be complement of what an XOR gate is. So this is how an XNOR gate works, or exclusive NOR gate works. So now let's see its truth table and a little bit about the input and output scenarios. Okay, so as you can see on the screen, XNOR, that is exclusive NOR gate, performs logical XNOR operation, which is exactly complement to an XOR operation. And you can see the gate symbol is exactly similar to XOR gate. However, in XOR we did not have this bubble over here. So this is an XNOR gate, and if I go to the previous slide, here you can see the XOR gate did not have this bubble over here, but our XNOR gate has this bubble over here. So that is the only difference in the symbol, and the output is exactly opposite or complement to the XOR gate. So let me read the output case, which is written in English over here. So output Y is high, that is the output Y is 1 if even number of inputs are high, else it is low. So this is exactly opposite to the XOR gate. So in XOR gate the output is high if odd number of inputs are high, otherwise it is low. So the output expression is given as follows. So Y is equal to A XOR B the whole complement, which can be even simplified to AB the whole complement plus AB, and A and B are the input values. Now taking the truth table into consideration, let's say A and B is 0 0, since even number of inputs are high, which means 0 number of inputs are high, right? So we don't have even one number which is 1, or one input which is 1, so that is 0. So 0 is even, or considered as even, that is why the output is high. Then these two, we know that odd number of inputs are high. So in the second case we have input B as high, in the third we have input A as high, so only one input is high, so one is odd, so that's why it is low. And then lastly we have both the inputs high, so two number or two inputs are high, so 2 is even, that is why the output is high. So this is exactly opposite to XOR gate, and if you've seen that video you can see in XOR it would be 0 1 1 0, and here it is 1 0 0 1. So basically that is the operation of a complement functionality which is offered by the NOT gate. So NOT basically just reverses the input. So that's how XNOR works. So this was the basic theory and the truth table as well as the output expression of a XNOR gate or an exclusive NOR gate. So yeah, that's it for this video, guys. This was a short video, but I wanted to cover the XNOR gate because it was requested by a subscriber. And if you like this video, give it a thumbs up, share it to your friends, and make sure you subscribe to this channel. Peace.
Hey, what's up guys, Tanmay here, back with another video for our channel Simple Snippets. So in this video, we'll be discussing about the universal gates, and in particular, in this video we'll talk about the NOR gate. Now I'll tell you what universal gates are in a while, but in the previous video, we saw the basic gates and also what logic gates mean. So if you have missed that video, you can check that out as well. So let's get started with today's topic, that is the NOR gate. The NOR gate performs logical NOR operation, which is exactly opposite to the logical OR operation. Now if you have missed the logical OR operation, you can check out the videos previous to this in this playlist itself, so that you get a clear idea about the basic Boolean algebraic operations. Now the output of NOR gate is high if both the inputs are low, and the output is low if any of the input is high. So this is exactly opposite to the OR operation. Now the expression is given as follows: Y is equal to A or B the whole complement, where A and B are the inputs. Here is the symbolic notation of the NOR gate. It's similar to the OR gate, but there is a bubble at the starting of the output. Here's the truth table, and as you can see, we have A and B as the input values. Then we calculate A or B and then take its complement. So it is exactly opposite to the OR operation. So now why is the NOR gate called as a universal gate? A NOR gate can be used to create an OR gate. So as you know, these logic gates can be connected to each other to form a big circuit. Similarly, these NOR gates can be assembled in such a way so that they operate like an OR gate. Again, NOR gates can be used to create an AND gate, and NOR gate can be used to create a NOT gate. Since the NOR gate simply can be used to create all these basic gates, it is called as a universal gate. So let's see how this is achieved in real time, wherein I'll show you on the screen and we'll prove the derivations as well. Okay, so as you can see on the screen, I have divided it in three parts. In the first part, we'll be proving the NOR gate to be working as a OR gate. Now we know the OR gate expression is given by Y is equal to A or B, but the NOR gate expression is given by Y is equal to A or B the whole complement. So how do we achieve that? Let's prove it. Now here you can see that there are two gates and both are NOR gates. Number 1 is over here and this is number 2. So they are connected to each other in such a way that the output of first gate is the input to the second gate. So let's see what the output of the first gate is. Now, the output of the first gate, as we know, is a simple NOR operation. So we have A or B the whole complement. Okay, so now this is again fed in as input to the second NOR gate. So here we will have A or B the whole complement, and again A or B the whole complement. Now consider this as A value and consider this as the B value. So this equation will be A or B the whole complement as the NOR gate performs, but here A is equal to A or B the whole complement and B is equal to again A or B the whole complement. So we substitute its values, we get A or B the whole complement or A or B the whole complement, and there is the whole complement above. So these two entities are equal to each other. Now we know A or A will give us A. We saw this law and it is known as the idempotent law. Now if you have missed the basic laws of Boolean algebra, you can check out the second or third video from this playlist and you will understand what exactly I meant. So this can be written as A or B the whole complement, and there is one more complement above. Now we also know that A double complement is equal to A. Now this is the double negation law. So this will give us A or B, and this is our final answer. Notice that A or B is a logical OR operation. So hence, using two NOR gates in this format, we have achieved the OR gate operation. So now let's see how NOR gate can be used as an AND gate. So here you can see there are three NOR gates connected in a particular fashion. This is the first one, this is the second one, and here you can see the third one. So for the first NOR gate, we provide A as the input two times. That is, we provide A over here and A over here. So the output would be A or A the whole complement, which is again equal to A complement. So as you can see, I have written the output over here. Similarly, we get B complement over here. Now the output of the third NOR gate would be as follows: A complement or B complement the whole complement. In the previous tutorials of this playlist, we studied the De Morgan's law, and according to that, we know that A or B the whole complement is equal to A complement and B complement. So we apply that law to this equation, which will give us A complement and again one complement and B complement and again one complement. So we consider these values as A and B. Now we know the double negation law, so this will again give us A and B. And there you go with the answer. So this is a logical AND operation which we achieved by a NOR gate assembly. So NOR gate can be used as an AND gate as well. So hence this is also proved. Now let's see the last case where we will see NOR gate which is used as a NOT gate. Well, the proof is very simple in this case. We provide A two times as an input to the first NOR gate, and there is only one NOR gate in this case. So the output here would be Y is equal to A or A the whole complement. Now we know A or A is always equal to A. So we can say that this is equal to A complement. So as you can see, we provided the input A, but we got the output as A complement. So this is the function of a NOT gate. So hence we have achieved NOT gate function using NOR gate. Now as all the three basic gate functionalities is achieved using simply NOR gate assembly, we can say that this NOR gate is a universal gate. That's it for this video. In the next video, we'll see another universal gate known as the NAND gate, and also see how it functions and achieves all the basic gates functionalities. If you like this video, give it a thumbs up and share it with your friends. Also, don't forget to subscribe to this channel so that you get notified when we upload the next videos. Peace! Hey, what's up guys, Tanmay here, back with another video for our channel Simple Snippets. So in this video tutorial, we'll see the second universal gate, that is NAND gate. In the previous video tutorial, we saw another universal gate which was the NOR gate. So if you have missed that part, you can check it out. So let's get started with today's tutorial. A NAND gate performs a logical NAND operation. Now this NAND operation is exactly opposite to the logical AND operation. Now if you have missed the basic operations, that is the AND, OR and NOT operations you can check it out in the previous video tutorials from this playlist. So the output Y of a NAND gate is high if any of the inputs is low, and output is low if all the inputs are high. I'll show you the truth table in a second. So this is the inverse of AND gate operations. Here's the output expression, which is given as A and B the whole complement. Now the symbolic representation is as shown. Now you can see the NAND gate is pretty much similar to the AND gate symbol, but here we have a bubble at the output line. Now this is a 2 input variable NAND gate with single output Y, which is equal to A and B the whole complement. Here's the truth table. We have input values A and B. So we first calculate the AND operation between these two variables A and B. And since it is a NAND operation which is opposite to the AND, we take a complement and get the final result in the last column, which is given by A and B the whole complement. So why is NAND gate called a universal gate? A NAND gate can be used to create the OR gate. That is, we can assemble number of NAND gates in such a way that we get the output of an OR gate. And lastly, NAND gate can be used to create the output of a NOT gate. So we'll see these operations in real time, and I'll show you how NAND gate can be used to create all these basic gates. Since a single NAND gate or number of NAND gates can be used to create these basic gates, it is known as a universal gate. So let's get ahead with creating these basic gates using these NAND gates. Okay, so as you can see, I have divided the screen in 3 parts. In the first part, we'll use a NAND gate and create a NOT gate. So let's get started with the proof. Now we have this NAND gate over here, and we supply an input A 2 times. That we supply input over here as well as here, and it's the same input, that is A. So according to the NAND operation or the equation of NAND, we have Y is equal to A and A the whole complement. Now we know that A and A is always equal to A. So this is the idempotent law, and we have studied this in the previous video tutorial. So if you have missed it, you can always check it out. So the output expression can be written as A complement only. Now notice that we supplied the value A and we got the answer as A complement. So this is the function of a NOT gate. Thus NAND gate can be used to create a NOT gate in this fashion. Now let's move ahead to create a OR gate using the NAND gate. Now here we have 3 NAND gates. This is the first one, this is the second, and this is the third. For the first NAND gate, we supply A as the input. For the second, we supply B as the input, and we get the resulting respective outputs as A complement and B complement. Now we know how we got these values, since we just saw that it is operating as a NOT gate in this case. But for the third NAND gate, we supply these values as input. So the equation of third NAND gate should be Y is equal to A complement, that is this value, and B complement, that is this value, the whole complement, because since it is a NAND gate, we have to take the complement of the entire equation. Now we studied the De Morgan's law, wherein we saw that A and B the whole complement is equal to A complement or B complement. So according to this law, which we apply to this equation, we'll get the value of the output as A double complement or P double complement. We've also seen that A double complement is equal to A. Thus the final equation I'll write it over here, will be A or B, or this operation is performed by a logical OR gate. Thus by using 3 NAND gates, we achieved the output of an OR gate. Now let's take a look at AND gate using the NAND gate. Here we have 2 NAND gates. This is the first one and this is the second. We supply inputs A and B to the first NAND gate. So we get the output as, so in this case we supply A and B as the input to the first NAND gate, and we get the corresponding output as A and B the whole complement. Now we supply this A and B the whole complement as input to the second NAND gate. We have A and B the whole complement over here, as well as A and B the whole complement over here. So the output of the second NAND gate would be A and B the whole complement and A and B the whole complement of the both two entities or the both two inputs. Now we know that A and A is equal to A. So this is the idempotent law which we studied in the previous video tutorials. So consider this entire part as A So even this part will be A. Now taking a logical AND operation will always end up with single value A. So this entire equation will be simplified to A and B double complement. Now we also know that A double complement is equal to A. So simplifying this equation further, we get A and B. Now this is the operation which is performed by the logical AND gate. So we just achieved the operation of AND gate using an AND gate. So that's it for this video tutorial. Now that we've understood the basics of logic gates, we saw all the laws, we also saw the De Morgan's law, we studied what logic gates are and saw the different types. We also studied the universal gates. So in the next video tutorial, we'll solve some numericals based on Boolean algebra and we'll derive some logic gates which are the results of these Boolean algebraic expressions. If you like this video, give it a thumbs up and share it with your friends. Don't forget to subscribe to this channel so that you get notified when you upload the next video. Peace. Hey, what's up guys, Tanmay here, back with another video for our channel Simple Snippets. So in this video tutorial, we'll be learning the concept of sum of products. Now if you don't know what Boolean algebra or Boolean algebraic expressions are, and you don't know about the laws or basics rules of Boolean algebra, you might want to check out the previous tutorials from this playlist. So let's get started with today's tutorial. In general, all Boolean expressions, regardless of their form, can be converted into either two standard forms. The first one is the sum of product form and the second one is the product of sum form. Now why do you need these standard forms? Standardization makes the evaluation, simplification and implementation of Boolean expressions much more systematic and simple. So that is the reason why we need these standard forms. Now the sum of product example is given over here. As you can see, we take the product of individual variables and then we have a sum between each of these terms. That is, we take the sum of these product terms. That is why it is known as sum of products. Now we'll see what product of sum is in the next video tutorial. Currently we'll just stick to sum of product form. Now here are some points to remember about sum of products. They can contain single variable. That is, as you can see, here there is only one single element and here there are 3 and 3 elements. So this is valid. You don't need another variable all the time. That is, we have a single variable but it is valid. Now in a sum of product expression, a single overbar cannot extend over more than one variable. Check this equation or expression. Here we have complement of two variables at a time. So this is not allowed in the sum of product expression. In this expression, as you can see, we have single complement, that is complement of a single variable. So this is valid. So let's see how to convert a non-standard Boolean expression into a sum of product expression. Okay, so I have written the question on the blackboard. Now as you can see, this is not a standard form, that is, this is not a sum of product expression. Since we have brackets involved, we need to open up these brackets. So here's the solution. If there are brackets involved, we first need to open them up. Now how to open up these brackets? We have seen the distributive law wherein we take the and we open up the brackets. So the solution would be A, B, or we need to take an AND operation between B and C and D, and we need to take an AND operation between these with a sum or operation in between. So the equation would be now this is the distributive law, and if you have missed it, we have discussed it in the previous tutorials wherein we see the laws of Boolean algebra. Now this is a sum of product form because you can see this is the one product term, this is one product term, and this is the third one. Okay, so now that you've understood the sum of products expression, let's see what a standard sum of product expression means. Okay, so far you've seen the SOP expressions in which some of the product terms do not contain all of the variables in the domain of the expression. That is, check out this case. Here in this product term, we are missing the variable C, and in this expression or in this product term, we are missing the variable A. So this is a sum of product expression, but it is not a standard sum of product expression. So what is a standard sum of product expression? A standard sum of product expression is the one in which all the variables in the domain appear in each product term. So the standard sum of product expression would be something like this: ABC or BCA or CAB complement. Now remember that complement of single variable is always allowed in all these expressions. So how do you convert a sum of product expression to a standard sum of product expression? Let's take an example. Okay, so I've written the question on the screen. Now as you can see, in this product term we are missing the term C, and in this product term we are missing the term A. So to convert this sum of product expression to a standard sum of product expression, we need to introduce these two variables in these product terms. So how do we go about it? Let's first write down that product term over here separately. Now remember, we have a law named complement law, which states that A or A complement is equal to 1. So I can first write this product term as AB and 1. Now we know AB and 1 is equal to AB itself. So why did I just write it? Now again I can write AB, and now this 1 can be represented by this value, and in this case it is C. So I can write 1 as C or C complement. Now this is due to the complement law, and if you don't know what it is, you can check out the videos from this playlist wherein we've discussed the laws of Boolean algebra. Now we need to just open up the brackets. So the further step would be AB into C, or we have to take a logical AND operation, or AB and C complement. So we introduce C by expanding this AB into two different product terms. Now similarly, we have to do this with this product term. So I can write CB and 1, which is equal to CB and A or A complement, which is equal to ACB or A complement CB. So I again expanded this term by introducing A, and I got two product terms. So the final answer of this entire equation can be written as, we expanded AB to these two parts. So I'll first write them: ABC or ABC complement. We didn't do anything with this part, so we just write it as it is, ABC or, and we expanded this product term to these two values. So I'll write it down over here, ACB or A complement CB. So this is not the final answer. Now notice that we have ABC, ABC and ACB, which can be always written as ABC. So I'll just change it. We have ABC repeated 3 times. So we know A or A is going to be equal to A only. So this is another law, and we have discussed it in the laws of Boolean algebra. So we just need to write it once. So this will simplify the equation and will give us ABC or ABC complement or A complement CB. So this was our first question, initial question, wherein we had the sum of product expression, which is given as AB or ABC or CB, and we converted it to standard sum of product expression, and the expression is as follows: ABC or ABC complement or A complement BC. That's it for this video, guys. I hope you understood the standard sum of product expression as well as the sum of product expression. In the next video tutorial, we'll see the product of sum expression and what standard product of sum expression means. We'll also see the conversion between the two. So if you have any doubts about this video tutorial, you can comment them in the comment section below. If you like this video, give it a thumbs up and also share it with your friends. Make sure you subscribe to our channel so that you get notified when you upload new videos. Peace. Hey, What's up guys, Tanmay here, back with another video for our channel Simple Snippets. So in this video tutorial, we'll be discussing about the product of sums concept. In the previous tutorial, we saw the sum of product concept, so if you have missed it, you can check it out. So let's get started with today's tutorial. In general, every Boolean expression can be denoted in two standard forms. The first one is the sum of product, which we saw in the previous tutorial, and the second is the product of sum, which we'll discuss in this tutorial. Now, why do we need these standard forms? These standard forms make the evaluation, simplification and implementation of Boolean algebraic expressions and their solutions easier and systematic. So that is the reason we need these standard forms. Now here's an example of product of sum. As you can see, we have two terms in this example. In the first term, we take the sum of two variables, and in the second term, we take the sum of these three variables, and in the end we take a product. So this means this is a product of sums. Now these two terms are known as the sum terms. Here's another example. We have this first sum term, we have a second term, and we have the third, and we take the product of these terms. So that is the reason why it is known as product of sums. Now here are some points to remember about product of sum. They can contain single variable, that is, this equation is valid one, wherein we only have one variable in the first term. So it is not compulsory to have more than one variables in each term. In a POS expression, a single overbar cannot extend over more than one variable. That is, check out this example. Here we take the complement of these two variables together. So this is not allowed. Again we take the complement of these two variables together. So this is again not allowed. But take a look at this example. Here we take the complement of a single variable. So this is a valid POS form. So let's say an example where we convert a non-standard Boolean expression to a POS form, that is product of sum expression. Okay, so I've written the question, and as you can see, we have this term and we have this individual term. Now this is not in any standard form. So by distributive law, we can convert this into a product of sum equation, which is given by A or C and B or C. We know the distributive law as follows. Now if you don't know the distributive law or the laws of Boolean algebra, you can check out the previous tutorials from this playlist. Now this is in a product of sum form. So now that we've understood the product of sum form, let's take a look at what is meant by standard product of sum form. A standard POS expression or a standard product of sum expression is the one in which all the variables in the domain appear in each sum term in the expression. So the equation 1 is a product of sum form, but it is not a standard product of sum form. That is, as you can see, in this term we are missing the variable c. So that is the reason why it is not a standard product of sum form. So what would be a standard product of sum form? Here's an example. Now in this case you can see these are the two sum terms, and both of them have all the variables a, b and c. So this is a standard product of sum form. So let's see how to convert a product of sum form to a standard product of sum form. Okay, so I have written the question, and we know that this is a product of sum form, but it is not a standard product of sum form, as in this term we are missing the variable b. So let's go ahead with the solution. So we first write down that term separately. Now this a can be written as a or 0. Now we know that a or 0 is equal to a, and this is the identity law. Now if you don't know these laws, you can check out the tutorials from this playlist wherein we've discussed the Boolean algebraic laws. Okay, so why did I write this a or 0? Now the 0 can be written as b and b complement. Now b and b complement is equal to 0, and this is from the complement law. So as you can see, you need these laws and you need to understand each and every law to solve these numericals. Now applying the distributive law, we get a or b and a or b complement. This is the distributive law. Okay, so we converted this single variable term to a double variable term wherein we introduced the variable b, and this is a product of sum form. This entire thing is a product of sum form, which is a standard product of sum form since it consists of both the variables a and B. So the final answer to this question, to this entire question, I'll just write it over here, would be A or B. This is the first term. We don't need to convert it, or we don't need to process it since it consists of both the variables. And now we converted this A to this entire part. So we substitute it and we get A or B, and A or B the complement. So this is our final answer after conversion of product of sum to standard product of sum form. So that's it for this video, guys. If you like this video, give it a thumbs up and share it with your friends. If you have any doubts or queries, you can always put them in the comment section below. Make sure you subscribe to our channel so that you get notified when we upload the next video. Peace. Hey, what's up guys, Tanmay here for Simple Snippets. Today we're going to learn and understand the canonical form of Boolean expressions, that is the min term and max term. Well, it is associated with sum of product and product of sum. So if you have missed those videos, we've discussed them in the previous two videos of this playlist. So let's get started with today's tutorial. Okay, so what are these canonical forms of Boolean expressions? Well, there are two forms, that is the min terms and max terms. Now min terms are essentially SOPs and max terms are product of sums, that is POS. Any Boolean function can be expressed as a sum of products, that is min terms, or product of sums, that is max terms. Well, as you can see in the table, we have three different input variables x, y and z, and their corresponding values of 0 and 1. So since there are three variables, we know the number of input variations is 2 raised to 3, which is equal to 8. So I have 8 rows with different values of input of x, y and z. Now the sum of product or the min terms, that is this part, is associated with the number 1. So I have written the equivalent values in the first row as x bar, y bar and z bar. So why did I write them like that? Since the initial values of x, y and z for this column are 0, we need to be converting them to 1 so that the product ultimately results in 1. Now when we take an AND operation between x, y and z, the only one case where the value is 1 is when all these variables are 1. So since all these variables are 0, 0, 0, we take their complements, which ultimately gives us value 1. Similarly, product of sum or max terms are associated with the value 0. So that is the reason why I simply wrote x, y and z. Since all their values are already 0, their sum will be equal to 0. Now min terms are denoted by small m and their position. That is, this is values at position 0, or you can consider this at the 0th row. So that is the reason why we say there is m0, and the associated x, y, z variables with their values corresponding to 0, 0, 0. Similarly, max terms are denoted by capital M with their corresponding value, that is 0 in this case, since at the 0th position we have all the x, y, z values as 0. Okay, so how do you express these Boolean expressions in these min terms and max term form? So let's take an example. Okay, so as you can see, I have written a question wherein they have given express function which is equal to a Boolean function and the value is a or abc in min terms or SOP form. Now in the previous tutorial where we understood the concept of sum of products, we saw in order to apply Boolean functions or apply the further processing, we need to first convert this equation into a proper standard form. So we need to convert this sum of product form into a standard sum of product form first. That is, we need to have b and c component in this term. So in order to do that, we need to associate it with the Boolean laws. So how do you go about the solution? Now we know this term is complete, so we don't need to do any processing on this. But I write this part separately over here and multiply it or take a logical AND operation with 1. Now why did I did that? In the next step, I write a and b or b complement. Now we know b or b complement is equal to 1. Now this is due to the complement law, which we studied in our previous tutorials, wherein we discussed the laws of Boolean algebra. So if you have missed them, you can check them as well. So this will give us the value a and b or a and b complement. Now we still need to introduce c in both these terms. So I do that. Now I'll write the answer over here. Okay, so we expanded this single variable term into this entire expression. Now we just need to substitute it at this place. So the final answer would be, the function would be this entire value plus ABC. Now notice that we have ABC 2 times, so we can ignore this part. Okay, so we've got our answer, and the answer is ABC or ABC complement, or AB complement C, or AB complement C complement. Okay, now we need to represent this in a sum of product or min terms form. So consider these values in the table as A, B and C, and see where A, B, C exist. So if we compare in the min terms, since we are looking for SOP, we need to see A, B, C would be this case. So it corresponds to M7. So I write M7 over here, or now I need to find A, B, C complement. So this would be the second last case, which is M6. So I write it over here. Now I need to find out A, B complement C, which is fifth case, this one. So I write that M5, and for the last one it would be M4. So this is how I represent a Boolean function in its canonical form of min terms. This can be also written as f is equal to just these values, which would give us summation of 7, 6, 5, 4. Now the reason why I wrote summation sign is because it is sum of products. So let's see how to convert these Boolean expressions into the form of max terms, that is product of sum. Okay, so as you can see, I have written the question wherein we need to express this Boolean function or Boolean expression in max term form, that is the POS form. So in order to do that, we first need to convert this into a standard POS format wherein we need to introduce an extra variable z. So how do we do that? Since we know this term is complete, that is it has all the variables x, y and z, we just need to operate on this term. So I'll write the term separately, that is x or y. Now the next step I do is I write x or y or 0. Since anything odd with 0 is equal to that thing, so that means a or 0 will be equal to a. Now this is due to the identity law, which we saw in the laws of Boolean algebra. So if you have missed it, you can check it out as well. Now I can represent that 0 with z or z complement, since z and z complement is equal to 0. Now this is the complement law. Now applying distributive law, we get x or y or z and x or y or z complement. So I expanded this term and introduced the variable z to get the standard POS format. So the final answer can be written as follows: f is equal to x or y or z and x or y or z complement and x or y complement or z complement. Now to represent it with these denotions or designations, I just need to find out where these values belong. So I can see here I have written x, y, z. So I can represent this with M0. Now I need to compare this with this table, and I can see that it is represented as M1, this part. For this term I have M3, so I write it as follows. So yes, this is the canonical form of max term. So it can again be simplified and written as f is equal to multiplication, that is product of sum. This is the symbol wherein we denote the product of sum or max terms, 0, 1, 3. So this is how you convert a typical Boolean expression to canonical forms, that is the min terms or max terms. So that's it for this video, guys. I hope you understood the concept of canonical forms and min term and max terms, since we'll be needing them in further tutorials as well. If you like this video, give it a thumbs up, and if you have any doubts or queries, you can always put them in the comment section below. Also do share this video with your friends, and don't forget to subscribe to our channel so that you get notified when you upload the next video. Peace! Hey, what's up guys, Tanmay here, back with another video for our channel Simple Snippets. So in this video tutorial, we'll be looking into a problem sum based on Boolean algebra. So if you don't know the laws of Boolean algebra and the basic rules, you might want to check them out in this playlist because we'll be needing the Boolean algebraic laws and basic rules to solve these numericals. So in this video tutorial, we'll be solving one numerical which consists of expression simplification. That is, it will have an expression which needs to be simplified. We need to draw its truth table and also its circuit design. So in order to do this, you need to first know what Boolean algebra is and also the logic gates and their basic operations as well as the laws of Boolean algebra. So as I mentioned earlier, if you have missed them, you can check them out in this playlist and we've uploaded those videos as well. So let's get started with today's numerical. Okay, so I've written the question on the screen which says that simplify the Boolean expression and draw its truth table and circuit design. So here's the Boolean expression. Now this f is a function which can be also denoted by q, that is the output. So we first need to simplify this expression. So let's start with the simplification process. First write down the expression as it is. Now the best way to start simplification is to look for brackets. And as you can see, we have one bracket term. So we first need to open these brackets. Now to open these brackets, we apply the distributive law. So here's how the equation goes. So what I did is, I multiplied or took a logical AND operation between this term and this term, which give me this term, and again I did a logical AND operation between this and this term, which gave me this term. So I have opened the brackets now, and this is by distributive law. Okay, so we've achieved one step and applied one law. Let's see how other laws get applied in the next step. So in this term, we have 2 times the variable b. So this equation can be further simplified as ab or bc or bc. So what I did is I clubbed these two values into a single value c and b respectively. This is because b and b is going to give me the value b itself, and c and c again will give me the value c. So this is due to the idempotent law which we studied in our previous tutorials. So I'll just write it down. Okay, so now we have simplified it further. Now here's the further simplification. AB or, now notice that we have BC 2 times. So we can again apply this law to these two terms and club them to write a single term as follows. This is again due to the idempotent law. So this is our final answer. Now you can further simplify it by taking b common, or you can keep it as it is. So it's your choice. Now if we take b common, we'll have b and a or c. So this is due to the distributive law. Actually we've reached our answer over here only, but if you want to take common and simplify it further, you can go ahead. So let's see the truth table for these values. Okay, so the first step of our numerical is done, that is we simplified this. Now we need to draw the truth table. So I'll just first write down these values. Now as you can see, there are 3 variables. So the number of input variations is 2 raised to 3, which is equal to 8. So let me just write down the input values. For the first variable a, I write down 4 times 0, then 4 times 1. For the second input variable, I write 2 times 0, 2 times 1, and I repeat it again. And for the last variable, I write 0, 1, 0, 1. So all the combinations of input are in these 8 rows. Okay, so the next component that I need is a or c. So I'll calculate that individually. Now if you don't know the logical and logical or operations and how to go about calculating the values, you can check out the previous tutorials wherein we discussed the basic Boolean algebraic operations. So the value for first row of a or c is 0. Similarly here we have 1. Let me just fill out the entire table. Okay, so now I've got this column. So now I'm interested in the entire output, that is b and a or c. So as you can see, I've written q over here, which is our final answer. So I need the truth table values for these. So I just need to take a AND operation between the variable b, which is over here, and this component that we just calculated. taking a logical AND between them. So I'll just calculate it. Okay, so we are done with the calculation and we have solved the second part of this question. That is, we have also calculated the truth table values. So now we just need to design a circuit. So for designing a circuit, we first need to observe the number of operations. Now I know there is a OR operation between A and C. Since it is inside the bracket, I first need to carry out that operation. So an OR operation is carried out by OR gate. Now if you don't know about the basic logic gates, we also have a video tutorial on this in this playlist, so you can check it out. So I'll just first draw an OR gate with two input values, that is A and C. So the result that I get out of this is A or C. Now I'm not done with the answer, I still need the value of B. That is, I have not calculated the entire answer. So this entire component over here is being ANDed or taken a logical AND operation with this component, that is variable B. So the output of this OR gate needs to be ANDed. That is, I need an AND gate. So I'll just draw the AND gate and pass the output of the first OR gate as an input to this AND gate. Now we need another input variable, that is B. So I'll pass it separately over here. And the resultant output would be our final answer. This is Y is equal to B and A or C. So now we completed the third part of this question and we have finally solved the entire question. Now the reason we simplify Boolean expressions is because if we calculate the circuit design and truth table for this entire expression, then it would be very tedious and the output would be finally the same. That is, this simplified version, which is over here, is equal to this version. So if you draw truth tables for this value and this expression over here, it will be the same. But in this case, we'll probably need more than two logic gates to design the circuit, and here we only need two. That is the reason why we simplify these Boolean expressions. So that's it for this video, guys. I hope you understood the numerical. If you like this video, give it a thumbs up and share it with your friends. Also make sure you subscribe to our channel so that you get notified when you upload the next video. Peace. Hey, what's up guys, Tanmay here, back with another video for our channel Simple Snippets. So in this video tutorial, we'll see another type of problem sum wherein we'll be given a Boolean algebraic expression and we need to prove the LHS is equal to RHS. Now this can be done in two methods, so let's see what they are. Okay, so as you can see on the screen, I've been given a question wherein I have to prove LHS is equal to RHS. This is the LHS part and this is the RHS part. So in the first method, we either start with the LHS or RHS and move on to the RHS or LHS respectively. That is, if I start with LHS, I will apply the Boolean algebraic laws till I reach RHS or vice versa. Note that in some cases LHS is not equal to RHS and we just need to find out. So it can be a trick question as well. Also you need to decide carefully which side you need to start. That is, you need to either start with LHS or RHS. Usually start with that side which has more variables or complex functions. Now in this case we know LHS is larger than RHS as there are more variables involved in this case. So I'll start with the LHS. So the LHS is as follows. So notice that in these two terms we have Z common, so I can take it out and it can be further simplified as X, Y or Z and Y or Y complement. Now this is by the distributive law. Now if you don't know the Boolean algebraic laws or these basic rules and operations of Boolean algebra, you can check them out in this playlist where we have discussed about these various operations and laws. Now the next step we get is X, Y or Z and 1. Now how did I get this 1? We know Y or Y complement is equal to 1. Now this is due to the complement law. So the next and the last step would be X, Y or Z, since anything and 1 is equal to that thing, and this is the identity law. Now notice that in each step we required a Boolean algebraic law. So these basic laws are very important in order to simplify equations and Boolean algebraic expressions. Now this answer that we reached of LHS is exactly similar to the RHS over here. Hence by method 1 we have proved that LHS is equal to RHS. Now let's see how the method 2 works. Now in method 2 we use truth tables to prove LHS is equal to RHS. So let me just fill out these values first. Now since you know there are three variables, the number of variations of input is 2 raised to 3, which is equal to 8. So I'll just fill out the input values. Okay, so I have filled the input values. So let's see what all components we need in LHS. We need XY, so I have written it over here. We need YZ, so I have written it over here. We need Y complement Z. For that we first need Y complement, which is in this column, and then finally I have calculated Y complement Z. Now for the LHS part, we need to make a OR operation between these three components. So I'll calculate that in this column. And for the RHS part, we just need XY and Z component, which is over here. So let me just calculate these intermediate values first. Okay, so I have calculated the intermediate values. Now for the LHS, as I mentioned earlier, I need to take an OR operation between XY, YZ and Y complement Z. So I'll just calculate the LHS. Okay, so I have calculated the LHS. Now I just need to calculate the RHS. For the RHS part, I need XY and Z, and I just need to take a OR operation between these two values. So I'll just do that. Okay, so I calculated the RHS. Now if you compare LHS and RHS, for every case, LHS is always equal to RHS. Hence by using method 2, that is the use of truth tables, we have proved that LHS is equal to RHS. So these are the two basic methods which can be used to solve problems wherein you need to prove LHS is equal to RHS or vice versa. That's it for this video, guys. If you like this video, give it a thumbs up and share it with your friends. If you have any queries or comments or suggestions, drop them in the comment section below. Also subscribe to our channel so that you get notified when we upload the next video. Peace. Hey, what's up guys, Tanmay here, back with another video for our channel Simple Snippets. So in this video tutorial, we'll see a problem sum based on min terms and max terms. Now, if you don't know what min terms or SOP and max terms, that is POS, are, you need to check out the video tutorials based on SOP and POS as well as min term and max term, that is the canonical form of Boolean algebra. So we have separate tutorials on these concepts because we'll need them to solve these numericals. So let's get on with today's tutorial, that is a problem sum based on these concepts. Okay, so here's the question. Find the sum of products, that is SOP or min terms, and product of sum POS or max term equations from the given truth table. So we've been provided with a truth table with the variables A, B and C, that is three variables, and we have given the output as follows, and we need to calculate the equations for SOP and POS. Now if you have checked out the video tutorials on SOP and POS as well as the min term and max term concepts, you must be knowing that SOP is associated with the output as 1. So from this truth table, wherever the output is 1, those input variables need to be considered to formulate the equation of SOP. So the function f for SOP would be as follows. Now to get the output 1, we have 0, 0 and C for this row. So to get output as 1, we need to take complement of A and B, and then we can take a product of these terms. So the first term would be A complement, B complement and C. Now notice that we did not take complement of C because its value is already 1. So for SOP, we need all values as 1. Now the second term is this, where we need to take a complement of A and C. Now since it is a sum of product, we have first product term. We need to take a OR operation, that is plus A complement, B and C complement. For the third product term, we have A, B complement, C complement, which is this. And for the last product term, we have A, B, C complement. Now we know the SOPs are denoted as small m with their positional value. So this function can also be written as summation of, since it is a sum of products, so we need to take a summation m1, comma, m2, comma, m4 and m6. Or it can be simply written as summation of 1, 2, 4, 6. So these are the three different types in which you can represent this SOP equation. So now let's calculate the functional equation of POS. Now POS is associated with the output as 0. So given in the truth table, wherever the output is 0, we need to consider those variables for formulating the equation of POS. So this would be A or B or C would be our first term. Since we need 0 as the output and we have all A, B and C 0 in this case, so we don't need to take complement of any of these values. So let's look at this case. In order to get output as 0, we need to take complement of B as well as C. And since it is a product of sums, we have the sum term over here we have the second sum term and we have a product sign in between, and it would be A or B complement or C complement. For the third sum term we have A complement or B or C complement, and for the last term we have A complement or B complement or C complement. Now POS are also denoted by capital M with their positional values, so this would be M0, M1, M2, M3, M4, M5, M6 and M7. So this equation can also be written as product, so this is the symbol for product, that is POS, product of M0, M3, M5, M7, or simply it can be written as 0, 3, 5, 7. So these are two different ways wherein you can represent a POS expression. Okay, so we are done with the solution. We just needed to calculate the equations, which we have done for both the types, that is SOP and POS. That's it for this video. I hope you understood the numerical. If you like this video, give it a thumbs up and share it with your friends. Also, don't forget to subscribe to our channel so that you get notified when you upload the next video. Peace. Hey, what's up guys, Tanmay here, back with another video for our channel Simple Snippets. So in this video tutorial, we'll be understanding the concept of K-maps or Karnaugh maps. In the previous tutorial, we understood the concept of SOP and POS and also saw some numericals on them. So if you have missed them, you can check it out, as we'll be needing those concepts in this tutorial as well. We won't be solving a numerical on K-maps in this tutorial, as we'll just understand what K-maps are and how are they used, and we also understand how to map a Boolean algebraic expression to these K-maps. So let's get started. We'll be covering the K-maps introduction and we'll understand the mapping of SOP expressions to K-maps. For this video tutorial, I'll be sticking to SOP expressions, but later on, I'll also discuss about POS expressions being mapped to K-maps. So let's understand some introduction or conceptual part of K-maps. A K-map or Karnaugh map provides a systematic method for simplifying Boolean expressions. Till now, we've been simplifying Boolean expressions using the different Boolean algebraic laws and techniques, but this is an alternative technique, and if you use it properly, it will produce the simplest SOP or POS expression possible, which is known as minimum expression. K-maps is an array of cells. It's similar to truth table as it covers all the different types of input values provided by the input variables, but it consists of a 2D array, and each cell represents a binary value. Now these cells are arranged in a specific way so that the simplification of a given Boolean algebraic expression is simply a matter of properly grouping the cells. That is, just by grouping these cells, we can simplify these equations. K-maps can be used with 2, 3, 4 and 5 variables. Beyond that, we have different techniques. Now the number of cells in a K-map is equal to the total number of possible input variable combinations. That is, if there are 3 variables, the number of cells would be 2 raised to 3, that is 8. So let's have a look at these K-maps. Okay, so as you can see on the screen, I have drawn a 3 variable K-map and a 4 variable K-map. Here are the variables A, B and C for 3 variable K-map. Now as you know, if there are 2 variables, we have 4 different values. So I have written them vertically, that is row wise. So 0, 0, 0, 1. Now instead of writing 1, 0, the way we write it is that we write 1, 1 first and then 1, 0. For the variable C, we have only 2 values. So the columns form as 0 and 1. So collectively, the address or the binary value for this cell, for the first cell, would be 0, 0, 0. Now the corresponding decimal value would also be 0. So accordingly, I will fill these values with their respective binary values. Okay, so I have filled the corresponding values of all possible combinations of the 3 variables A, B and C. So now let's take an example of a Boolean expression. Here you can see I have written question 1, wherein we have to map the following SOP expressions on the K-map. So now we know SOP is associated with the number 1, that is, all the variables having 0 value needs to be complemented and converted to 1, 1, 1. So the value of this cell would be A complement, B complement and C complement, since all the variable values are 0. Now if you have missed the part where we discussed the SOP and POS, we have a separate video wherein we understand its concept and we convert different Boolean algebraic expressions into SOP and POS forms in the previous video tutorials from this playlist. So you can check it out as well. So now with that concept, we need to map each of these terms into the K-map and represent it by number 1, since it is SOP and it is associated with the number 1. So the first term ABC means that all values are 1. That is, we don't need to take any complement. So the cell value where we have 3 times 1 is number 7 or this block. So I write 1 over here. Now A complement BC means we need to find a cell value which has value 0, 1, 1. So this is this cell value. And for A complement, B complement, C complement, we need to find a cell value wherein all values are 0. So this would be this cell. So I mark it with 1. So we have mapped this entire Boolean expression to its corresponding K-map format. Now let's have a look at this expression. First, let's understand the 4 variable K-map. We have the variables A and B that form the row and C and D that form the column. So A, B can take 4 different values 0, 0, 0, 1, 1, 1 and 1, 0. Similarly, CD can take the 4 different values 0, 0, 0, 1, 1, 1 and 1, 0. So collectively the cell value of this cell, that is the first cell, would be 0, 0, 0, 0. So let me just fill out all these cell values. Okay, so I have filled all these values. So let's map this expression number 2 to its corresponding K-map values. So for the first term A, B, C, D, we need to find a value that has the binary value as 1, 1, 1, 0. So that would be this block, that is the number 14. So I mark it with value 1. For the next block, we need to find a block that has the binary value as 1, 1, 1, 1, which would be this block. For the third product term, we have all the values as 0. So that would be the first cell itself. And for the last product term, we have 0, 0, 1, 1. So that would be this block. Okay, so I've mapped this as well. Now notice that both these equations are standard SOPs. That is, every product term has all the 3 variables ABC, ABC, ABC. And for the 4 variable, we have ABCD, ABCD, ABCD and ABCD. So whenever we map a Boolean expression to a K-map format, we first need to convert it into a standard POS or SOP format. So just keep that in mind. When we actually solve these problems, we'll have to do that calculation as well. So this was just for the mapping. I'll discuss about grouping, adjacency and simplification in the next tutorial. So that's it for this video, guys. If you like this video, give it a thumbs up and share it with your friends. If you have any queries or comments, post them in the comment section below. Don't forget to subscribe to our channel so that you get notified when we upload new videos. Peace. Hey, what's up guys, Tanmay here, back with another video for our channel Simple Snippets. So in this video tutorial, we'll be solving a 3 variable K-map. In the previous video tutorial, we saw the concept of K-map and why it is used, and also saw the mapping process. So we did not solve a numerical based on K-map in that video. So in this video, we'll cover that part as well. Now for this video tutorial, we'll be solving a 3 variable K-map and we'll be looking into 3 concepts, that is mapping, grouping and simplification. So let's get started with today's tutorial. Okay, so as you can see on the screen, I have a 3 variable K-map drawn and I have a SOP expression which I need to minimize using the K-map. So let's start with the mapping process first. Now we have to map each of these SOP terms to its respective cell value in the K-map. So let's see the first term. The first term is A complement B complement C. Now the binary value corresponding to this product term is 0, 0, 1. Now how did I get this value? I have drawn a truth table over here with the corresponding A, B, C variables and their input values and the respective min term values. Now as you can see, wherever there is 0 in the input, we have a complement over here. That is, if there is a complement of the variable, that value corresponds to 0. And if there is no complement, it means that it is 1. So I need to find out the cell value with this binary value, which is this one. And now since it is a SOP expression, I mark it with value 1. Now let's take a look at the second term. A complement B complement C complement. Now as you can see in the truth table, we have the first min term M0 with this value, which is 0, 0, 0. Now the cell value in K-map corresponding to 0, 0, 0 is the first one. So I again mark it as 1. For the third term, A, B complement, C complement, we are looking at the cell value which is 1, 0, 0. So that would be this cell value in K-map. So I mark it as 1. For this term, A, B complement, C, we are looking at a cell value which is 1, 0, 1. So that would be this cell value. And for the last term, that is A complement, B, C, we are looking at cell value 0, 1, 1. So that would be this one. Using the truth table and the binary values, I have mapped this entire expression to the K-map format. So wherever I have written a 1, it corresponds to a product term or this term. Now we are done with the mapping. Now let's see the concept of adjacency. As we know, K-map is comprised of cell values. So this is cell 1, this is cell 2, so on and so forth. Now each cell is adjacent to each other in a pattern. That is, this cell is adjacent to this one, that is to the right of it and below it. But this cell is not adjacent to this one. That is, diagonal adjacency is not possible in K-maps. So these two cells are adjacent, these two cells are adjacent, and these two. Now the first cell over here, this one, is adjacent to the last one. Similarly, this cell is adjacent to this cell. Now the concept of adjacency is required when we group these cells together in order to simplify the variables. So we'll move ahead with simplification of these Boolean expressions. Now the reason we understood the concept of adjacency is because we need to group these values which we have marked as 1. Now the groups are supposed to be formed in 2, 4, 8 or 16, that is in the power of 2. So we cannot form a group of 3 or we cannot form a group of 5. We always need to form a group of 2 to the power n. And while grouping, we have to see that we have to form the group of the largest value. That is, if we have a group of 2 as well as 4, we have to consider the group of 4 first. I'll show you in a minute how it works. So let's take an example in this sum. Now as I mentioned, this cell is adjacent to this cell and this cell is adjacent to this cell. So if I form a group of these two values and these two values, that would be invalid or that would be redundant. Instead, I can form a group of these entire 4 values. So this is our first group. For the second group, I have this one separate over here, so I need to group it with some variable. So I form a group of 2. Now if I cannot group it with anyone, I have to write it separately. That is, it forms its own group. So currently we have 2 groups. The first group is of 4 variables or 4 terms and the second group is of 2 terms. So after grouping, how do we go ahead and simplify? So let's see for first group what all binary values we have. For the first group we have 0 0 0, we have 0 0 1, we have 1 0 0 and we have 1 0 1. Now the way we simplify these is we look for the common term. That is, in all these 4 different rows, which variable value does not change. So as you can see, the value of b remains 0 throughout these different iterations or different records. So I write it separately. And since it is a 0, I write a complement over here. So this is the output for this group. That is, if you simplify these 4 values or 4 terms associated with these cells, you will be remaining with the answer B. Now for the second group, we write the values separately. We have 0 0 1, we have 0 1 1. So as you can see here, we have 2 variables A and C whose value does not change in these 2 records, and B changes, that is B is 0 in the first record and B is 1 in the second record. So we exclude that, we take a OR and we write down these common terms, and since A is 0, we need to take a complement. This is a SOP, and guess what guys, this is our final answer. That is, if we simplify